Now I assume that you already finished the installation of qiskit and then already started the Jupyter. And then let me show you with the some introduction to the qiskit. So qiskit is the as I mentioned is a language to program originally for to program the IBM quantum system. And then because we already installed the qiskit package, so you should be able to import this one, and then this kind of command will show you the version informations like here. And then it takes a while when you first started your kernel, and then you should be able to see all of these information. And then the rest of the part is tutorial adapted from the this one. And then the this is not a required convention, but personally I prefer to use the namespace. And then if you are not familiar with the concept of the namespace, then in the object oriented language, because we might have there is a lot of chance that you will use the same name for different purpose. And then in that case, the name will be it has different meaning depending on the context. And then to make sure that you won't get mixed those things, then there is a concept of the namespace. So instead of just importing the entire thing from the qiskit package, if you just import the qiskit as a QK, then you should be able to distinguish different names, even with the same name, you might not have any collision in terms of the name. And another convenient tool is the NumPy, and then this is mainly for the calculation, for the arithmetic parts. And then for matplotlib is the most popular plotting library in the Python. And then currently this inline means that once we do some kind of once we do some kind of plotting, whether that plot will be embedded inside this notebook, or we will have just a independent or a separate window later. So that's those kind of thing will be determined here. Yep. So so the first thing we want to do is build this kind of circuit, and then I already showed you how you can do this with the web interface. Now we want to do it with the programming. So the first part, once you imported the qiskit, the first class you will use is this quantum circuit. And then in this case, we specifically specify that we will deal with 3 qubits. So that's here. And then once we call this, once we instantiate this class, then we will obtain some quantum circuit object inside here. And then once we do this, then we will have just the 3 lines of the qubits, but it does not have any information. So the first thing we have to do is add the Hadamard gate, and then because each of them has the number like 0, 1, 2. So if we want to add the Hadamard gate to the 0th qubit, then what we have to do is use this kind of H with the parameter 0. And then this part, and then this method is the part of the object of the quantum circuit. And then once we do this, then we might we are wondering whether our programming is properly done. And then in that case, what you can do is use the draw method of the quantum circuit object. So if you just do this, let me just run this one by one. So yeah, I'm just evaluating each of the cell, and then yeah, if I here I'm still pressing the shift enter, but because these two types of the cells are um, the um, the mark markdown cell, so they won't be evaluated. And then if I just keep pressing, and then now I'm in the code cell. And then in this case, if I press the shift enter, then they will be evaluated. And then yeah, and now I'm adding the Hadamard gate to the 0th qubit. And what I want to do is I want to visualize the current situation. So what I have to do is call the draw method of this object. So if I just press shift enter, then now, yeah, as we did, only the Hadamard gate is added to the 0th qubit. Now, what we want to do is add these two CNAC gates. And then the CNAC gate is between 0 and first qubit, and 0 and the second qubit. So the syntax for that CNAC gate is that the first, yeah, and then yeah, in this case, instead of calling as a CNAC, what we do is flipping the bit, and then flipping the bit corresponds to X gate. So yeah, sometimes CNAC gate is also called as a controlled X gate, and then in this in qiskit, yeah, it is called as a controlled X gate. And then the first bit is the control bit, and then the second parameter is the target qubit. So the first one is acting 0th qubit is controlling the first qubit, and then the second CNAT gate is 0th qubit is controlling the second qubit. So all I have to do is just type these two lines, and then I have to evaluate this cell. So if I do the evaluation, and then if I do the drawing, it will show a draw figure like this one. And then yeah, this is still reasonably good, but if you want some fancy figure, then what you can do is use the matplotlib library. So MPL means is the acronym for matplotlib, which we mentioned in the here. And then matplotlib was already imported when you are importing one of these. So if you call this, if you use this method with this MPL option, then you will actually obtain this fancy looking circuit. Now, if you want to save this kind of image, then what you can do is just to use the save fig of the, once you store the image in the in one of the variable, and then save the figure, and then the new file will be created in your working directory. Yeah, and then the one thing, I want to emphasize one more time is that in the last lecture I mentioned that even though we are we have a tendency to consider this one as the first qubit and second qubit and third qubit, if we consider each of these index as the power of the 2, meaning that this can be considered as 2 to the 0th, and then this one can be considered 2 to the first, and then this one 2 to the second. Then in terms of the binary notation, binary number notation, the value of this guy will appear as the first bit or most significant bit, and then this qubit will appear as the least significant bit. Yeah, so make sure that you don't get confused in terms of the ordering. And then the so this part basically explains the order part. And the next thing is that as I showed you in the previous lecture, we can also use the quantum circuit simulator. And then there are a few different types of the quantum circuit simulator. And then the first type is called as state vector backend. And then this is what you would expect when you learn the up to now in the class we always discuss about what will be the resulting quantum state. And then quantum state is the, and then quantum state will be generally represented as psi equals something, some alpha with some kind of basis, and then another basis, and then so forth. So yeah, this kind of description is called as state vector representation, and then what you will obtain as a result of this state vector backend is the information of alpha, beta, and gamma, and so forth. So all those probability amplitude information. So to use the state vector backend, what you have to do is import the error package from the qiskit, and then what you have to do is get the backend whose type is the state vector simulator, and then store that that object in this variable, something like this one. And then once it is done, then what we can do is, because we store the new circuit created here in the circ variable, so what you do is provide that circ variable as the first parameter, and then the state this simulator backend as the second parameter. And then with this one, once you execute, then it will create a new job, and then the job is being executed. And then for this case, the circuit was too simple, so the execution, the simulation won't take too long. But just in case you have very long job, then what you can do is use the job status, and then it will tell us what how is the job doing. So in this case, the job is already finished, so you will obtain and then you should always make wait until you will get the until you will check that the job is done. And then once because now we have our job is done, then we can obtain the result of the that execution, and then that result will be stored in this variable, and then we can obtain all those details of the result. So result get a state vector will give us the
말씀하신 내용을 웹에서 검색해드릴.
Sorry about the noise. So so now we obtain the state vector information, and then if we just print out, then we will just have this complex number in front of 0, 0, 0 and 1, 1, 1, and then the rest of them will be 0. So that's why we have all 0 for the rest of them. So let's see. Okay. So, and then this is all. This is complete by itself. This information gives all the information we need. But sometimes it is easier to visualize. It is easier if you can visualize your quantum state. And then one option is to plot the probability. So if you use the instead of recasting the state vector information, you can just recast the count, and then if you plot the probability, then you will obtain that this point half probability for 0, 0, 0 and the half probability for 1, 1, 1. Another type of the backend is called as a unitary. So in the previous example, the result the result of the simulation is the state vector. However, yeah, if we have any circuit like this one, then if we assume that the initial, we don't know about the initial vector, initial state, then the rest of the part can be imagined as the unitary transformation. So that's why it is called as a unitary backend. And then yeah, in this case, we have to also create the object for the unitary simulator, and then similar to the previous case, you can just use the backend unitary backend as a second parameter here, and then run the job, and then you should be able to obtain the entire unitary transformation. And the unitary transformation will be appear as the form of the matrix. So that's why you obtain this unitary this kind of matrix representation. Another option is that is called as open QASM backend, and then in this case, the quantum state we are expecting is this one, but in the real life, yeah, in the real experiment, what you obtain is not yeah. So you know that your final state will be in this state vector shape. However, the result of the but in the experiment, what you obtain is not this ideal abstract quantum state, but you actually obtain the measurement result. And then you know that if your final quantum state looks like this one, then your probability to measure either 000 or 111 will be half. So if you just repeat the same experiment or the run or a shot, we sometimes call it as a shot. And then if we just repeat the shot multiple times, then what we obtain is either 000 measurement or 111 measurement with the equal probability. So that's what we are doing here. So yeah, again, we just created the same circuit again here, but here, yeah, one difference is that now we also started to add the classical bit. So in the previous lecture, I showed you that to store the actual experiment or actual run, then eventually we will obtain some kind of classical information, and then we also need to define or declare the classical variable. And then yeah, in this case, the first three means these three qubits, and then the second parameter 3 means the 3 classical bits. So yeah, we by doing this, we declare this part, and then by calling these 3 lines, we created this line, and then now yeah, I added the new barrier, and then finally we added the measurement, how it should be measured, and then this 0, 1, 2 means the quantum bit, qubit 0, 1, 2, and then this 0, 1, 2 means the classical bit 0, 1, 2. So yeah, they will be just mapped to each other, and then yeah, the current situation is also, and then we can also draw that kind of situation or visualize the circuit. And then now we also want to run this circuit with using the QASM simulator. So yeah, the syntax are almost the same as before, but yeah, in this case we also want, and you also need to make sure that you specify the number of trial. So again, this is equivalent to measuring this at the end. Yeah, it is equivalent to measuring this kind of quantum state. And then when you are trying to measure this quantum state, then you will either only you will occasionally get yeah, with the half of the with the 50% of probability, you will measure either 000 or 111. Yeah, so that's and then over 1024 trial, were shot, yeah, you will obtain 0, 1, 0, 0, 0, or 1, 1, 1, yeah, and then they might just appear randomly, and then eventually the balance will be the number of the shots to obtain 0, 0, 0, and then 1, 1, 1 will be almost balanced. I said almost because it is uh, probabilistic process. So we actually don't know when we will obtain 0, 0, 0 or when we will obtain a 1, 1, 1. So yeah, if I just run this job and then yeah, obtain the result, then what it says is 0, 0, 0 appeared 524 times. So the ideal case is this will be uh, 512, but somehow, yeah, 0, 0 was obtained more often than 1, 1, 1. And finally, yeah, if I just plot them in terms of histogram, then we basically obtain the probability like this one. And another way we can represent the current as some kind of quantum state is using the black sphere representation. You are already familiar with the concept of the black sphere. And then, unfortunately, black sphere representation is only useful when we are discussing about the single qubit. But yeah, so yeah, in this case, I just drew the single qubit. And then in this, yeah, and you can still run it with the state vector simulator, and then the result, yeah, with the result you can either plot with the histogram, but another option is using the block sphere. So you can just use this function, plot block multivector function, and then you will obtain this one. However, yeah, and now if you are familiar with the concept of the matplotlib, then another option is not just using this static figure. What you can do is instead of, yeah, so previously I declared this one as the matplotlib inline, meaning that all the figures will be embedded inside the notebook. But if I change this one as the Qt5, then yeah, it will actually open a new window. And then where is that? Sorry. Yeah, so after you evaluated this cell, and if you run this cell one more time, yeah, you can either run it here, go here, or you can just do it here, and then yeah, you will obtain the new yeah, it will open a new window, and then in some cases this figure window won't pop up out of your Jupyter, the rest of the Jupyter part. So if you don't see any of the new window coming out, then make sure that they will check here, yeah, and then yeah, you will be able to see this one. And now what you can do is, because this is independent plot or independent window, so you can actually manipulate this this window, this figure. If it is embedded, then yeah, embedded in the as a part of the notebook, then this is not manipulatable. But yeah, with the independent plot, then this is kind of advantage of having using the Qt5. But for the rest of them, I will just stop doing this. So I will go back to the inline, and then you will see that this yeah, once I go back to the inline, then this window will go away, will be closed. Okay, so yeah, that's one of the useful tip. And then now what we are going to do is oops, sorry. No. Yeah. So yeah, we will now what we are going to do is, yeah, previously we were only using the circuit simulator. Now what we are going to do is submit the job to a real hardware. and then you already saw how to use the real hardware in the with the IBMQ website, but then you can also do the same thing using the using the qiskit, and then there is some kind of guideline or tutorial to how to obtain the IBMQ credential. And then in this case, all you have to do is go to your once you already created your credential in the IBMQ, then you will actually obtain you actually have this token for your API or for your use. And then one option is you just copy this API by pressing this button, and then now the token is copied, and now I can apply. And then the first thing you have to do is import the IBMQ from the qiskit package, and then the next thing you have to do is save your credentials or this token. So here, and then here you can see that this is the markdown cell. I have to change it to the code cell by pressing Y, and then now what I have to do is write down what I just copied, and then if I just because I already copied here, using by pressing this button, so all I have to do is just to press the Control V, and then now here is my credential. And then all I have to do is press the Shift Enter. Then my IBM token is saved in my local computer. And now you actually don't need to do this anymore because it is saved in some of the file internally on my laptop. And then next time when you are using the IBMQ, all you have to do is just to call this load account, and you actually don't need this information. So what I can do is just erase the entire information, or just to go back to where I used to be, and then I will just make this part as the markdown type. So that I won't actually run it later. And then next time all I have to do is again load my account, and then the first thing I can do is check what kind of backends I can use. And then these are the list which you also could see in this website. So I was able to use all of this. And then one of the way, so previously when we were using this interface, what I did is after I created the circuit using the composer, and before I start to run, then I chose one of the least busy server backend. Now, it can be also done by qiskit. So what I have to do is just run this code, then it will find out the least loaded or the least busy backend, and then it is now we found that IBMQ Quito is the least busy. So and then if I just evaluate, then it will give me the information of the IBMQ Quito. And then let's see, what is the quantum volume? It has the 16. So, and then let's see how does this work? And then before I start, I run on that server. Let me also try to use the Quasm simulator on the IBMQ. So all I have to do is just run this code, and then now I obtain the IBMQ Quasm simulator, and then the type of the sorry, looks like I just copied and paste one more time. So now what I can do is run the this IBMQ Quito, and then well, actually I just check the status of this one, and then finally I submit the new job to this machine, and then in this case the type of the circuit I'm going to submit to that um, job. That job is that this not single qubit, but where is the circuit? Sorry about this. Yeah, so this new circuit, and then yeah, here is a new circuit, and then this will be sent to the this the backend we chose here. And yeah, let's see. Yeah, so if I submit, then the once the submit is successful, then I will obtain this job object, and then I can just check the status of my job. And then currently, my job is in the queue because there are other people who are trying to use, and then yeah, I have to wait until it is running, and then probably we will the running is done. So now I can expect that I can obtain the result of job. So yeah, with this command, I will retrieve the result, and then yeah, if I print out, it looks like this one. So in principle, I'm only assumed to obtain 000 or 111 in the ideal case. But I always kept saying that the current status of the quantum computer are not ideal. So there are a lot of errors. And then yeah, if I want to visualize the current situation, then I can also plot the histogram one more time. And then as you can see here, there are yeah, even though, yeah, these are supposed to be zero point 0.5 and 0.5, and the rest of them are supposed to be 0. However, you can see that there are a lot of errors. So even if the sum, if you add these two together, the summation is only above, slightly above, yeah, something like 82% or 83% ish. So the rest of them are around, yes, 18% or 17% of error. So that's huge. A lot of errors are there. Yeah, so that might be a little bit um, disappointing, but that's kind of limitation of the IonQ. And yeah, there is also another interesting algorithm which I did not cover in the class, but you can also read the introduction of this Bernstein-Vazirani algorithm. And then in this case, what we can try is that yeah, one of the simplest idea about the Bernstein-Vazirani algorithm is it is similar to the Deutsch-Johnson algorithm, not exactly the same, but it is instead, if you are given some kind of hidden binary string, then yeah, how many times do we need to try until we can actually figure out this one? And then classically, then you have to at least try n times if you have a n bit. But in quantum mechanically, you can figure out the result just with the single trial. And then that's what this means. And then such kind of situation can be represented as a quantum circuit. So I defined the simple function which will generate the new Bernstein-Vazirani circuit. Yeah, so yeah, if I actually run it, then this is version of 3 case, especially when the secret key is 011. So yeah, that means that the and then in this case the 011 is assigned in from bottom to up. So the first qubit, yeah, won't do, and we won't do anything for the first qubit, but the second and third qubit will do syndicate around here. And then if we just want to know what will be the result, then yeah, the first option is to use the QASM simulator, which will give us the exact result. So yeah, if I just run it with the job and then job is done. So if we check the result, then as you can see here, the result we obtain is 011, which was the same as original string, which was 011. So just by, yeah, even though, yeah, we assume that this is kind of black box, or in other sense, it is an oracle. And then even if we don't know about this box, just by trying single shot, we should be able to figure out the this internal of the this black box. So that's the point of the Bernstein-Vazirani's algorithm. And then, yeah, as you can see here, yeah, when we tried 1024 times, then we always get 011 for this case. And then, yeah, of course, histogram will be boring. Then, yeah, we also want to increase the situation to the 8 qubit. So I increase the n to the 8, and then the pattern for the secret key is even more yeah, this is quite random, but it is some kind of secret key. And then if I just repeat what I did, then this will generate the new quantum circuit for the Bernstein-Vazirani algorithm. And then so this is the circuit, and I also want to make sure that this circuit is correct. So yeah, what I can do is run on the Quasm simulator, and then once you do that, then you can also check the result. And then yeah, now yeah, we can also confirm that the result of such kind of execution of this kind of circuit will always give us the original pattern like this one. And then yeah, if I just plot the histogram, then it will be again boring, simple histogram. Then what happens if I just try the same algorithm with the real device? So yeah, now it becomes interesting, and then I need to figure out what kind of backend I should use. So yeah, this kind of line will find out the least busy, but which can satisfy our requirement. And then if you look at this circuit actually requires all 9 qubits. So my requirement is that the number of qubits should be either larger than equal to 9. And then if I just run this, then there are only one machine which can satisfy this requirement, because I'm still under the free free account. And then in this case, the only this machine, Melbourne, has the qubit more than 9, or yeah, more than or equal to 9. So yeah, I do not have any option. So that's why I just am assigned this machine, Melbourne, and then their connectivity or configuration looks like this one. But unfortunately, the quantum volume of this machine is really low, like 8. So what can we get? What can we expect? Let's see. Yeah, so I just ran the job, and then I'm actually waiting until the job uh, um, will be done. And then yeah, there was some yeah, I had to import some library which I forgot. So now yeah, I have to import this line, and then job monitor is checking the status of my job periodically with the interval of 2 seconds. And then you can of course change this one. And then yeah, it is showing yeah how many jobs are queued in the in IBMQ. and then yeah, because I don't want to wait too long, so yeah, I will, yeah, I actually, yeah, and then now it is the order is decreasing, and then yeah, I will wait until it will be done. But in the meantime, I will also switch back to switch to another machine, which is called as IonQ. So yeah, so up to now, what I just showed you was the introduction or tutorial of the qiskit, and then IBMQ I'm also running the demonstration with the IBMQ. Another thing I will also show you is the IonQ, and then in this case, yeah, so IonQ is another machine which yeah, which is shown here. So yeah, IonQ is based on the ion trap technology, and then the current available number of qubits are only 11. So you might think that the power or performance of this one is lower compared to what you just saw in the with the IBM. Yeah, because IBM already has the 15 qubit. So you might underestimate the performance of this machine. However, if you actually go to if you see the result of this machine, then you might think otherwise. So yeah, let me just show you how you can use this machine. So you will do the same thing with this machine. So all you have to do is yeah, start with these lines, and then um, yeah, yeah, about the documentation, all you have to do is just to go here, and then here you will be find out the different types of the service provider, and then if you are interested in the more documentation, then you can also go here, and then there is some kind of explanation, and then all you have to do is install additional the package, and then yeah, according to the tutorial or the uh, instruction here, then what I have to do is make sure that the qiskit version, the qiskit Terra version is larger than this value. So what you can do is, instead of opening the command prompt like here, and then adding installing with the PIP, another option is you can just use this um, um, this exclamation symbol with the command. Then it is equivalent to running the command in the command prompt. So the first thing is you have to make sure that the version is up, updated. And another thing you have to do is actually installing the qiskit IonQ package. And then I assume that if you just do it once, then you don't have to do it again. Yeah, but yeah, I'm just including this part for your um, so that you can actually see this case. And then if you want to use the IonQ server in Korea, then it is and then IonQ is not public service yet. And I shouldn't say yet because they actually have no plan to make their machine available to a general public for free. But yeah, so it is a little bit different from IBM policy, because what IBM did was they initially made one of their first machine available to everyone for free. So people were exposed to the concept of the quantum computer, but the IBM IonQ is not at such kind of stage yet. But their machine is quite powerful. So in Korea, the um, government funded some of the contract with the IonQ. So if you want to use the IonQ, then what you have to do is go to here, and then there is some kind of description. But this one actually does not tell you how to apply for the account, but regularly we will yeah yeah this quantum support center will accept the application for using the IonQ, and then um, um, if there are enough number of students who wants to use the IonQ, then I will make an arrangement that the students can also get the credentials for to access the IonQ machine. But here I will just give you the demonstration with my account. So what you have to do is similar to the IBMQ, and then here yeah, I forgot. Yeah, so yeah, for this case I have to run this one more time because I ran this notebook in other environment, and then this is the demonstration because and then for this demonstration, I have to run these parts one more time. And so in my environment now, the IonQ qiskit is also installed. Now I can run this, and then I should not have any problem. And then to use the IonQ hardware or server, you need to write down your insert your access key here and run this line. And because I have only my own access key, so I will just execute this line and then could get back to this. Yeah, so I cannot show you my access key in this recording. So I will just pause the video and then run it with my credential, and then yeah, I will put this my access key again back here. So yeah, I just ran this line with my secret key here. So yeah, now yeah, it is recognized, and now I can check what kind of backends are available in the at the IonQ, and then yeah, this one also shows that IonQ has the its own circuit simulator and then real hardware, which they call it as a quantum processing unit (QPU). So yeah, let's yeah first try with the the software simulator, and then here I'm using the same example like before with the qiskit or IBMQ case, and okay, so I don't know, yeah, how many people are using this. Well, it looks like there are a lot of jobs still being queued. And then yeah, so this is the status of the IBM machine, and then now I'm using the IonQ in this page, and yeah, so if I run, yeah, so this is the same circuit which I showed you before with the IBM case, and then now I'm also doing the same thing with the IonQ simulator, and then what yeah, you can either use this execute command, or you can also use this run command, but it looks like this command seems to be more preferred way to use. So let me just delete this cell, and then if I run, then yeah, then I can also check the job status, and then now it is done. So I can also obtain the result, and then this will show us how many times I got 000 versus 111. And then if I also calculate the probability, then they are almost 50-50. But yeah, because it is a random process, yeah, it will take a while to obtain very close points, 0.500. Then you have to run it so many times. Yeah. And then now, yeah, I will also show you the result with the IonQ server. Yeah, so again, if you show the list, then there are a simulator or the real QPU. And then now I'm using the real QPU. And then, yeah, of course, if you want to run this job, then you actually have to use this line. So if yeah, currently I made this one as a markdown cell, but I can just change to the code cell, and then now you can just run this job. And then yeah, one of the reason I printed out the job ID is it actually takes a while until you will obtain the result. And as you can see here, yeah, similar to the IBMQ. IBMQ now I have there are still 6 more jobs queued in front of me, and then unfortunately IonQ seems to be even worse. Yeah, because and then you can also check the rough status of the IonQ machine, and then if you click this one, then you will be redirected to here. And then currently the average time in queue is sometimes as high as 3 hours today. And then yeah, it actually takes a while until yeah, depending on how many people are using. But yeah, when I tried this morning, yeah, still the situation was not so good. And then it is still the case for today. So unfortunately, I won't have enough time to wait until everything will be done. So what I did was I already ran the same circuit on the IonQ machine this morning. And then for this job, yeah, let me just cancel this job because the yeah, I will tell you later why. Yeah, I'm canceling this one. Yeah, at the end. Yeah, so I just canceled that job, and then yeah, but this is the job ID I ran this morning, and then one option is I can retrieve the result of this morning's job. So yeah, what I can do is to retrieve the previous job, all I have to do is put this job ID in here and then retrieve the job. Then I can actually obtain the result from the previous case. And then now I can just do the same thing like here. So in that case, what we obtained is that the 0, 0, yeah, so in the ideal case, what we are expecting is the 0, 0, 0 and 1, 1, 1 will be the only result, and then all the others will be 0. And unfortunately, it is not the case. But if you look at the probability, then they are actually more than 95% success. And if you compare such kind of result with the IBMQ, yeah, and then it was around 82% success, and then the 18% of failure were the error. And then in this case, it is again around 90 above 90 yeah, above 96. So the error is less than 4%. So that's somehow the advantage of the ion trap. And then another test is the Bernstein-Vazirani algorithm. So I actually repeated the same step like before. Yeah, so yeah, I just copied the code from the this IBM case, and then I also reproduce, and then you will obtain the same result. And then if you run this circuit on the IonQ simulator, then you will obtain this. Yeah, one of the change here is for the IBM case, yeah, I generally use the execute. Here, I'm generally using run because there is some issue with the execute. Yeah, so but yeah, in principle, yeah, it should not be so different. Or and then if I just yeah run this, then yeah, I should be able to get the job status, and then did I? Yeah, and then yeah, if I just keep checking, then I will obtain something like this one. And this one looks a little bit different from what I showed you with the IBMQ, because for the IBMQ case, I got only single 011, while for the IBMQ, yeah, it might look like I got two types of the possibility, but that's not actually true, because um, when I try the same circuit with the IBMQ, yeah, so in the IBMQ, yeah, the one of the differences for this case, I had only 3 classical bits, because in the original Bernstein Vazirani algorithm, you actually don't need to measure this fourth qubit. So yeah, and then yeah, the only information you need is the result of only these 3 qubits. So I actually tried the same thing on the IonQ first, but then there was some error. So the only way I can make the entire circuit to run is that measure all the qubit, even though I'm not interested in the value of this qubit. So because I always measure the this first qubit, or the most significant bit out of these 4. So, and then depending on the this run, sometimes this value will become 0, or sometimes this value become 1. So that's why I have the correct sequence. Yeah, so originally the sequence was 0, 1, 1, and then the result shows that I actually got the 0, 1, 1 correctly in the lower 3 qubit, 3 bits, but the first bit is sometimes 0 or sometimes 1. And then this is because we actually in the original algorithm, the value of this one doesn't matter. So yeah, yeah, the best way is not to measure this one. But again, yeah, when I tried, then there was some error. So I unfortunately, I just had to measure both of them, both of the cases, or I have to measure all of these qubits. So, but at least I got this result. And then um, now, yeah, you can see that you obtain these 2 cases, but the summation of these are actually 1. So that means that the lower 3 bit 0, 1, 1 and 0, 1, 1 will be always 0, 1, 1. So that's what we are expecting, yeah, because that is the hidden string we are expecting. Now, yes, similar to the case of the IBMQ, I increased yeah. Let me check what is the Q status. Oh, it is still 6 times. My order is 6. So yeah, I don't know when that one will be done. But anyway, yeah, let me also run. Yeah, so what I did was I also ran the yeah, ran this I also increased the number of bit to 8 for the Bernstein-Vazirani algorithm, and then this is the hidden string I use. And then if I just apply this, if I just create a new circuit, then yeah, I obtain the exactly the same circuit like before, except that I actually had to have this additional measurement part. And then I can also run it on the classical simulator. So yeah, if I do that, then if I check the job status, then it is done. And then yeah, again, yeah, I will have always these two possibility. But what we have to consider is the summation of these 2 probability, and then they are 1. So now, yeah, we can also try the same thing with the real device. And then again, yeah, I'm just using the IonQ QPU, and the number of shots are 4,096. And then, yeah, again, I can also submit this job. but as I mentioned, yeah, the response of the IonQ was extremely slow today. Yeah, especially today. I don't know whether yeah it is the case in other days, but yeah. So yeah, I actually ran the job in this morning again, and then the result of such a job or the job ID of what I did in the morning was this one. So yeah, here I can retrieve the value by using this command or this line. And then I'm just showing what I got this morning. And then okay, yeah, I don't need this. And then uh, and I obtain these um, results. And if I plot this case, then you might think that this is well. So if you look at carefully, then these two cases corresponds to these 0, 0, this one and this one, and then the rest of this noisy part corresponds to wrong measurement. So yeah, there is still some error. And then if I just try to figure out how much the success case compared to the failed case, then we had about 10% of error. So you might think that that's already too large. However, yeah, here, yeah, it is still slow. Yeah, so unfortunately, I might not be able to show the result of this trial, but I also did the same run in the morning today, and then these are the results I've got, and yeah. So let me just copy this part. Oops. Yeah. So yeah, I also should have saved the job ID of this one, but IBM's response was relatively quick, so I did not save it for the future. But anyway, yes. So why is that working? Oh, the reason this cell was not being evaluated was because I was running this job monitor. So yeah, because it was running. So unfortunately, yeah, to continue, I had to stop, interrupt this cell evaluation. So now I have this result stored in the counts, and the correct case corresponds to only, yeah, and then yeah, I wanted to figure out how many times we succeeded in obtaining the original hidden sequence or the secret key. Yeah, so our secret key was where is that? Yeah, so this was our secret key. So I wanted to figure out how many times we succeeded. So that's how I, yeah. So this one I can obtain calculate the success probability, and unfortunately it was only less than 0.2%. It is not 2%. It is less than 0.2%. And then if I just plot the entire result, and then yeah, you will obtain, yeah, it takes a while, and then yeah, it is completely messed, and then I even cannot see any details. So what I had to do is I switched from inline, I switched to Qt5 from inline, and then yeah, if I just try to replot histogram, then it will actually create a new window. And then now, yeah, I have this independent window. Then I can at least zoom in or manipulate this part. And then, unfortunately, you might hope that these two, this case or this case corresponds to the correct answer, but it is not the case. Yeah, it was somewhere around here. And then yeah, this morning I checked, but I cannot. I don't know whether I can reproduce that case. So I can, if you zoom in, then there are a bunch of errors, wrong measured case. So yeah, and then if you just calculate, and then this is the estimation, and this is the result. So for this machine, the success probability was less than 1%, while for the IonQ, the success probability was around 90%. So why do we get such kind of completely different, or why do we have such a big difference in the performance or accuracy? That's because of the quantum volume. Because yeah, as I said, the quantum volume of this guy is only 8, while the quantum volume of IonQ, yeah, I don't know the actual number for the IonQ, but for the current machine, but their other machine, they recently claimed that they achieved up to 4 million, like quantum volume. So it is completely different domain. And the main reason why we have completely different quantum volume is because of the connectivity. Yeah, so when I talked about the quantum volume, I said the connectivity between the qubits um, play a important role. And then here, this figure, what this figure means is that we have 11 qubit with the IonQ, current IonQ device. IonQ is planning to upgrade their machine to 32 qubit within this year. Yeah, that's what they claim. And then in this case, even for one qubit is directly connected to all the other qubits, like here. Yeah, so yeah, it has one-to-one connectivity to every pair. However, if you look at the IBMQ website, then yeah, for example, this Melbourne has only the connectivity in this only these a few. Yeah, so for the superconductor conducting qubit, their layout is generally in two-dimensional space. And then in that case, you probably, yeah, let's say that you have, yeah, let me also open some other qubit case. So here, yeah, again, I don't have any access to this machine yet, but as you can see here, it has 65 qubit, but on the other hand, most of the qubits are not directly connected to each other. So, for example, if you want to do any quantum operation between this guy and let's say this guy, how would you do? The first thing is you have to swap, and operation. And then if you have this kind of two-dimensional layout, then this will be kind of limitation, because you don't want to make a line like this one from here to here to all the others, and then that's yeah. So and then IO trap actually does not have such kind of limitation. So that's why we didn't have any trouble with the, yeah, we didn't have a big problem or a big error with the IonQ device, while yeah, IBM machine has a lot of trouble. And this situation is not different with other types of implementation, like a quantum dot or yeah, MV center. So yeah, this is the power of the or advantage of the ion trap. So yeah, yeah, probably I will give you more overview about the ion trap probably at the end of this semester. Then I will stop today's lecture here.